Hello, welcome to session number 22 in the series Unlock Circuit Design using ADS. My name is Anurag Nigam, and what I'm going to present to you is a operational transconductance amplifier. So, why do we need an operational transconductance amplifier? Operational transconductance amplifier. So now the question is, why do I need this? Okay, so we know that the response of a op amp has got the corner frequency omega p1, and this omega p1 is given by 1 over the input resistance R1, which is basically R1. So G1 is equal to 1 over R1 equal to GDS4 plus GDS6. Okay, so if you remember the naming convention on an op amp, or you can refer to my older video. So now the issue here is the gain stage, okay, is this one, right? And this is the load, right? So basically, okay, so that's the story here. And then you have got the what you call the Miller capacitance. So that Miller capacitance will be R2 GM7, right? R2 GM7 times of C, which is the compensation capacitance, right? So that's the Miller capacitance. So that's the relationship. Now in this case, if I want to take omega p up, okay, so there is, of course, I cannot touch the gain, and the gain is GM7R2. So of course I cannot touch this one. So this one I cannot touch. Now the next comes is the capacitance. Okay, so this capacitance also I cannot touch. So I'm left with only R1, or rather G1, right? So now the question comes is, if you want to make omega p1 large, then you have to reduce R1, right? So this is what has to happen. Now this in R1 I cannot touch GDS4 because it's a gain stage. Now if I was to keep this, right, so if I was to keep this in parallel with GDS6, right, so basically in this case this is equivalent to RDS4 in parallel with RDS6. I cannot, of course I cannot okay, so now in this case the only way I can improve omega p1 is by reducing R1. That means if I reduce RDS6, right, if I reduce RDS6 to be a very small number, right, then R1 basically will go down, and that will push the omega p1 to be going out in frequency, or to a higher frequency. Now the question comes is, if I have a low impedance node as the load, then what happens to the gain? Well, the gain is supposed to go down, right? But there's another way of doing this. If I was to mirror that current, so if you say that there is a differential stage, right? So if there is a differential stage, right, and I am not going to see the load over here, I am going to push that, so I'm going to mirror out that current to another stage which is seeing a high impedance on the output node, right? So if I do that, so let's say this is my gain differential stage, and if I use a load here and then split that, so I have a cascade load, right? So if I can split the load into two, And so this current swing I transfer, so if this is I1 I2, then the swing I1 minus I2 I am going to mirror out to another, this one, I1 I2, okay, other differential pair. So this becomes a folded cascade, right? So now the cascade is folded, and there on the output node I am going to have a high impedance output node, and that way I'm going to translate I1 and I2 into basically the output voltage. So what it means is I'm going to have a single stage only. Okay, I'm not having a common source here, is it? Mm, let's see. Okay, so I transfer the impedance to the output node in this branch, right? And my output impedance is going to be high impedance, right? So that way I can transform the gain to be high. Now I was doing this with a what you call, I was doing this with a common source. I was going differential in, and I was having single ended out. Now I am not going to have a common source, but my gain is gonna go up, right? And so still it's a single stage, it's a single stage gain stage op amp, but then I have an independent control of the current and the resistance, load resistance. So that way I'm not compromising the gain. So I can get a higher gain out of a OTA with a much higher omega P1, right, than a normal op amp, and it's still a single stage only, because the input transistors are doing a current swing, so it is not going to give you a voltage gain. It is only giving you a current gain, like a transconductance, and then that current is transformed with a mirror to the output, and then the output node is a high impedance node, and I am using that high impedance node multiplied by difference of current, or the input differential input current, and then getting an output. So that way my omega P1 shifts out, as well as I can have the gain to go up. So let's go ahead and design this OTA. So I'm going to make a I'm going to take a okay I'm going to make a new schematic, and I'm going to call this one as OTA 1, let's say, right? Create. Okay, and I'm going to copy a cascade current mirror from the common gate, from the cascade amplifier, right? So I am going to go here in gain stages. There is a cascade amplifier. Okay, so I am just going to copy this guy, these two, and these two, right? So I'm going to copy that, right click, copy, and I'm going to paste it over here. Okay, let me make sure that I'm recording this. Sometimes I forget. Okay, so now this is a cascade current mirror. Let me just quickly complete the circuit. So this is diode connected here, 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 there you go. Okay, so this is a cascade stage, but I am dividing it into half. Now the question comes is, how am I dividing this into half? Okay, so what I'll do is I'll take these, right, and okay, so in this case this is a 1:1 mirror, so these are also 20. So this is just a 20, and this one is going to be, no, I'm doing something wrong here. So this is 1:10 current mirror, right? And let me just do the connections here. So this one goes here, and this one comes to this node, and out of this, so this is 1/4 the size of these two, right? So I'm going to pull in same current, which is 20 microamperes. So I'm going to pull out 20 here, and I'm going to pull out 20 here, right? So I'm pulling out 20 microamperes over here, 20 microamperes, sorry, 20 microamperes over here, and I'm going to pull out 20 microamps over here, 20 microamps over here. Now, so this is my cascode current mirror. Okay, so now this current which I have over here, right? Okay, so so what I'm going to do is I'm going to create another one over here, right? So I'll pull them apart, right? And I'll take this and repeat it. So this is that, and I'm going to mirror this one. This is over here, and this connection I'll do later on. So this is the same mirror, right? F5. Okay, over here. Okay, so I'm put back this connection over here. So I am having two currents which are mirrored out. Okay, next I am going to take this one and move it out like this, correct? And what I'm going to do is I am going to repeat this one. So I am going to repeat this one, flip it out like this, and this connection I'll do later. So let me just get rid of this connection. Okay, so I have these which I would F5, move the text over here. Okay, so now I have folded the cascode. I'll show you how. So this is over here, and this connection is over here, correct? So now I am going to put my gain stages. So the gain stages I'm going to put is half the size, because this is a PMOS, right? And I'm going to make it a NMOS, right? Right. Why would this connection be over here, right? This, okay, I'm folding it out, right? So this connection goes over here. Okay, so whatever is the current flowing here, that's going to be mirrored out here, right? And this variation in current I will cause using a NMOS. So let's put a NMOS, this one, edit, copy, and okay, so edit, paste. So this is the input stage, so this is my input stage, right? And I am going to have F5 here. This one and this one, correct? Okay, and I'm going to make this one as half. So let's make this one as 10 and this one also as 10. So this is my input stage, and I'm going to pull out a certain current out of this, right? So okay, so I need to pull out a certain current out of this. So let me just repeat this one. Okay, so this one I'll make as, let's say, 4, and I'll tell you why I'm doing that in a bit. It will become clear. So I am going to pull current out of this node. That's the tail current, correct? And let's ground this. Okay, so now this cascode is folded out, right? And another thing I can do, okay, that would be that I am going to put in here, okay, this connection is fine, but I'm going to hang 2 more transistors over here for improving the slew rate to provide more current to these branches. So these are going to be NMOSes. So I'm going to take one NMOS. So let's take that NMOS over here, correct? And then basically I want to draw current out of this, right? So I'll take 2 NMOSes. This is called, you are improving the slew rate of the OTA, because these are going to provide you more currents into the 2 legs. Okay, so here it goes like that. Let's bring them close. F5. These texts are going to kill me. So let's make a small transistor, let's say 2 here. That will be sufficient for enough current enhancement, right? And then I'm going to connect this one over here. This is the body connection, and this one over here, and I am going to draw current out of the, so I'm going to drive it with this, nothing special in this. So these are all same nodes, and this is going to assist current on these 2 legs, correct? So this way my slew rate can be improved. Okay, so having done that, what I'm going to do is I'm going to construct this half, and this half is also going to be a kind of a cascode, right? Okay, so I'm going to just repeat these transistors here and tie them together. So I'll take this transistor and I'll repeat it. Okay, so over here I have repeated this transistor, and again for the other lag I'm going to repeat the same transistor, right? So this is repeated here, and then I'm going to take that and repeat it to be a cascode like that, correct? And this one I am going to do twice the size, 8, and let's say 8. Okay, so now I have another cascode over here like this. Okay, So now these are tied together. Okay, and this is driven by this because it's a cascade, right? And this is tied with this one, correct? And then I am going to have uh, I'm going to have 1/4 the size, isn't it? So just 1 second. Okay, so 1/4 of this size would be, so I'll just repeat this one. So 1/4 of this size. So let me just mirror it out. So this is 1/4 the size. Okay, so let's make it 1/4 the size. F5. So if this is 8, I make it 2. Okay, so this is 1/4 the size, right? And this one, okay, uh, is diode connected. So this one is diode connected, and these are all connected together. So these are grounds, correct? And this one is diode connected, and this is driving this node. No, yeah, yes, that's correct. So this is driving this node. So now we are all set, and this is connected here, and this is connected here. So now I have the input currents difference, which will be generated by the input signal, will be translated to the output through 1:1 mirror, which is a folded cascade here, and then there is a high impedance node which is VO over here, right? And then this is driven by almost half the current. So this is driven by almost half the current. So I will drive this with the current here, because this is an NMOS. So PMOS is going to, so this is half the current, so the overdrives are going to balance. Okay, so now we are ready with this op amp. This is the output node, and then I can put some compensation capacitor, right? So the output node would have a compensation capacitor across here, right? So what I'll do is I'll put here a C, lump components, a C of around 0.2, 0.3 or something like that, and then look at the margin and adjust it. And then I want a R. I will put at 1000 or something, or 1 kilo ohm, correct? And this is how I'm going to compensate this OTA. Okay, and over here I am going to have 0.2 or 0.3, and then I'm going to have 1000 ohm. 1, 2, 3. Okay, so this is still a single gain stage, right? But then there is a current gain which can be applied over here. If you want, you can always scale these transistors to have more currents flowing this way, and that way you can bump up the gain. So there is a voltage gain stage which is a cascade here, and then there is this current gain stage which is the input stage, right? So having said that, let's try to test this. Okay, so I am going to have this output node named as VO. Sorry, again note that this is something which cannot drive a resistive load. It would need a follower, right, to drive resistive loads. Okay, so it would still need a follower. Okay, so now I'm going to put the inputs. So I'll go to sources, frequency domain, VAC, and here I am going to put only 0.5 as the input, because the other 0.5 is going to come from the differential, right? And then there is a VCM which is 1.2 roughly, center of the supply. So I'll put this as VCM so that later I can adjust VCM if I want to. Okay, so this is VCM. Apply. Okay, let's have a voltage across it. Apply. Okay, so this is there. This is my input. And then I am going to have another differential input, right? So I'm going to have another input over here, right? Okay, and this is going to be 180 degree out. 180. Right, so let's see. Okay, so we are all set. I'm just going to make a connection here. Okay, so we have given the connection here. Now let's see what's happening here. There is a supply which is left, and that supply is 2.4 volts, right? So I'm putting VCM as the one has half the supply voltage. So I'm going to put here sources frequency domain, and this is going to be 2.4 volts. Okay, so let's make this 2.4 volts. Two 0.4 volts, and VCM is a variable, so I have to create a variable here, and I will call this as VCM, V common mode, VCM, and I'm putting this VCM as 1.2 volts, right? And hopefully, if everything looks correct to me, I have to put in an include file from the library files, correct? And then I have to do here AC simulation, right? So I'll go 1 kilohertz to 10 gigahertz in steps of 80 points per decade. So I'll go to simulation AC, and I will put here this one, and I will go from 1 kilohertz to 10 gigahertz as a log scale with 80 points per decade, or if I want I can put 160 points per decade, 160 points per decade. And in the display I will adjust the decade to be displayed. So this is what's the excitation. Okay, so now I'm going to hit a simulate button. If I have done everything right, I won't have to debug it, but if I have done something wrong, I might have to debug it. Okay. Okay, it's complaining about some node which is floating. I don't think there is a floating node. Let's see. And here I am going to put a log scale on x-axis, and there you go. Okay, so let's see what kind of gain do I have here. I have 46 dB gain here, and let's look at the 3 dB frequency. Sorry, 3 dB frequency. Okay, 46, 43.1, 43.1. Okay, so now I have 5 megahertz in an op amp. What did I have? Let's put a phase also. Phase. Okay, and here I am going to put here unwrap. Unwrap. Okay. Okay, so here it becomes 0, but then it is rolling from 0. That's okay, so I'm not going to look at that. Okay, so what do I see here? Up to 5 megahertz I can go, and if I look at the same thing with the uh, sorry, if I look same thing for a op amp, so let's look at the response of a op amp. Okay, 3 stage gain stages op amp, 3 stage or 2 stage op amp. Okay, we are at 400 kilohertz as a corner frequency, and over here we are at 5 megahertz. Now let's make another variation of this. Okay, this OTA. So what I'm going to do is I'm going to say copy cell, right? OTA 2. So I'm going to do OTA 2, copy cell, and I'm going to create OTA 2. Okay, and I'm going to improve overdrive and lower GM and see what happens. Okay, so what I'm going to do is I'll go to OTA 2, and everywhere where I have 260 I'll make it 130. How's that? 130. Okay, so nothing is changing. The gate lengths are the transistors are becoming twice the size and half the length. Okay, so 130, I'll quickly do it. 130, 130. Okay, 130. Bear with me. This is just a clerical job. 130. Okay, so it's just I'm trying to sacrifice gain for certain more bandwidth. That's all what I'm trying to do here. 130, 130. So I'm sacrificing gain for bandwidth. 130. So everything looks 130 here. 130. And over here, this is 130. And this is also 130. Right? And this is 130. So bear with me this clerical job. I could 130. I don't know how to speed up the video. I don't have tools to do that. 130, 130, and 130. So what has happened over here? I have just made everything to be 130. Yes. And let's lower this current slightly for gain advantage and hit simulate. Okay, let's look at the output and let's put a log scale on x-axis. Okay, so this is a lower gain, 36, 33. So we have gone slightly up in frequency. Let me see if I'm recording it. Yes, I am. Okay, so let's simulate this. Okay, so there is a warning here, so let me put a marker here. 37 dB gain, new 34. So I have to look at 34, isn't it? 34.7, 34.7. It's roughly over here. So we have gone up to 40 megahertz. Okay, I just changed this capacitor down, right? So That's the story here. Okay, let's see. 1600. Okay, I'm just going to change the compensation values. Nothing happens over here. Okay, so this is our OTA 2, and let's look at whatever the best frequency I can get and best gain. So this is OTA 2. Let's look at OTA 1. Okay, so let's look at OTA 1, which is twice the length. And over here, let's bring this down to here, just to 600, and bump up the current gain by increasing these sizes. Okay, so I'm bumping up the current gain and I'm halving the slew. 1.2. It doesn't do much here unless you look at slew rate. 1.2. Okay, so now let's say simulate this again. Okay, so I have 47 dB gain. So let's see. 46, 45. I have to go to 44.4. 44.4. So roughly 11 megahertz is my 11 megahertz is my first corner. It's at 11 megahertz, right? Zero crossover is over here. Okay, so it is 11 megahertz roughly. Okay, so now this OTA can be used as to a much higher frequency. So I'm going to make a component out of this, right? And also OTA 1, but for this one I'm going to keep the current sources inside, so that in my higher hierarchy I don't have a problem, right? Let's see if I'm recording. Yes, so I'm going to make a component out of this. Okay, so I would just save this as OTA1C. Copy cell. So C stands for component. OTA-C. In the same op-amp circuits, is it? Yes. Okay, so I have OTA-C. So I'm going to make a component out of this. So first of all, I'll throw out this. Okay, delete that. Okay, so this is my non-inverting input. This is my inverting input, right? And this is my VDD. And I am going to combine all the grounds together, not separate grounds. Okay, so these are all my grounds. So this will go off, of course. This will go off, and this is going to be ground, so this will go. So I'll connect all the grounds together, so there's no confusion. So grounds are done. Now what I want to do is I want to have pins here. So I'll have VDD, I will have ground. So ground is over here. So that's the ground. And then I have got inverting inputs and non-inverting inputs. So this is a non-inverting input. So I'll put that as NINV. So that's a non-inverting input. And then I have an inverting input INV. And that's the inverting input. And then I have an output, which is VO. And that's that, VO. So we are all set with the component. So I'll just make a schematic for this. This is a common mode voltage. I'm not going to touch that, keep it inside. and I'll just make a component out of this. So let's make a component of OTAC. So I'll just say new symbol, say create symbol, say OK, escape, right, and I just want a symbol for that. So I'll use this as a symbol where I will have inverting at the top. So okay, so I have it over here as the inverting input, and then I have a VO over here, and then I have a ground connection over here, and then I have a VDD. Over here. Okay, so this is my OTA, right? So to distinguish it, I'll put in a text and say this is a OTA 1. OTA 1. Okay, so that's a OTA 1. So I'm going to use this symbol for further circuits. So next thing I'm going to discuss in next session is a what you call instrumentation amplifier. And instrumentation amplifier is used a lot in case of bridges in measurements, right? So I'm going to do an instrumentation amplifier next in the next session. Thanks a lot.